today. I'm going to wrap this up today. And this is about some of the constraints that come in designing this flow control system and what that ends up meaning as far as what are actually the kind of the set of viable designs for this semi-automated or flow tracking dose controller. So here are the constraints. The flow has to be laminar in the dosing tubes. Minor losses have to be small. And in order to get minor losses to be small, it requires both that the velocity has to be low and that the minor loss coefficients have to be small. There's going to be a limit to how small you can make the minor loss coefficients because there has to be an entrance to a tube and there has to be a change in diameter at the end where it's exiting. And so there are going to be some expansion or contraction expansion losses. So there's the equation for those losses, that the losses in those tubes are a minor loss coefficient times v squared over 2g, where v is the velocity in the tube. And then the left-hand side is this pi error times head loss. Head loss is what is the total head loss you want to have through that tube. And you need just a tiny bit of that total head loss to be due to minor losses. So pi error might have a value of 0.1, which means that the losses that are due to minor losses could be at most 10% of the total losses. So this is like engineering. In the ideal world, we would just have no minor losses, and then our system would be perfect. But we can't actually do that. There are going to be expansion losses somewhere in our system, and so we just have to set a constraint on them to make them be small enough so that the errors that we get are okay with us. And just a reflection that it took us a number of years to figure out how critical that constraint was. The third big bullet point, dosing tube has to be a reasonable length. It's very easy to design a system where the dosing tube has to be like 7 meters long. And if the dosing tube is 7 meters, I don't know, 22 feet long, that would mean that you would have to find a place in your water treatment plant where there's somewhere where there's a 22-foot long stretch where you can put this straight tube. And that becomes annoying because there aren't many walls that are that long in a small plant. And so finding a design that has dosing tubes that are a reasonable length ends up being a constraint as well. And all of this requires some good engineering. So I'll have, some questions about how do we actually get to a viable design. So I don't know if you'd like thinking in terms of graphs and equations and curves. This is just to illustrate like how this system works. And the graph is head loss on the y-axis as a function of flow rate on the x-axis. And of course, as you increase the flow rate, the head loss increases. So these graphs all go up. So that should make sense. There's more and more head loss as the flow rate goes up. And the red line is the dream world. The red line is what would happen if there were no minor losses. If there were no minor losses and we just had the beautiful Hagen-Poiseuille, it's laminar flow in a long straight tube. That's beautiful. But that's not what's actually happening. So the reality is the blue line. In addition to the Hagen-Poiseuille term, which is the major losses, there's also a minor loss term. And that minor loss term is where the KE, the minor loss coefficient, is showing up in that equation. And that results in a line that is no longer straight, it's curved. So you see how that blue line slowly curves up. And that's the quadratic effect of the q squared term in that equation, because now there's both a q term and a q squared term. And then the way that we're thinking about design, and you could think about modifications to this, but the way we're thinking about design is that we take the point at the maximum flow rate and we pretend that it's linear from there to zero. So the green line is our simple linear model of how we're going to represent this, even though you could think about a better fit, but it's good enough. And that's the green line equation, where we're just making, instead of a quadratic q squared, we're holding the 1q constant, and so the 1q that's being held constant is we're pretending that q max was always equal to the maximum q, and that equation overpredicts the head loss for the entire range, but it's close to reality, and what that makes clear is that what we're trying to do is design a system where the gap between the green line and the blue line is small enough that we're okay. That the plant operator, when they're setting the coagulant dose, they're not going to be frustrated by the dose not responding at all the way they expected it to when they make a change. So that's one perspective on this. Another perspective is, well, what size tubing would you actually use for those doser tubes? The doser tubes, remember, they're the resistors that create the head loss and that create this linear relationship between flow and head. So this graph is maybe a little entertaining version of what happens when you put all the constraints together. So the one constraint was that it had to be laminar, which means that the Reynolds number has to be less than 2,100. And you just take the Reynolds number equation, and the Reynolds number equation has a V in it. And we get rid of that V and instead put Q over A in it. And then we solve for, okay, and A is pi d squared over 4. And then we solve for that D. And when you do that, you get the red equation, that D min laminar is equal to 4Q max over pi times the kinematic viscosity times the maximum Reynolds number. And that constraint, we have to, let's see, that is a minimum diameter. We have to be above the red curve always in order to be in the laminar range. And the next constraint is the blue constraint, which is about the minor loss error. And remember, in order to get minor losses small enough, you have to make the velocities be lower, which means that it helps to go to a larger diameter. A larger diameter will reduce the velocities. And so the minimum diameter that's required to get you a low enough minor loss is also a minimum. So that's plotted there in blue, and we need to be above the blue line. And what's interesting about that is that for the range that's of interest, the blue line dominates. So that was what we hadn't initially realized when we were creating this design. Blue line dominates. That's the real constraint. It's not the laminar flow that's the constraint. It's keeping the minor losses small. That is the real constraint. And then there's one more thing, and that is when you go to a hardware store, there's a limited number of different internal diameters of tubing. And so here I've said, let's suppose that we can have the tubing that's in green. So 2/32 of an inch is 1/16 of an inch internal diameter tubing. 4/32 is 1/8 of an inch internal diameter tubing. So like it's a little over 3 millimeters. So those are some tubing sizes, and that creates the green curve. So the green step function says that for flows between 0 and something like, I don't know, 0.8 or something, I could use a 1/16 inch diameter tube. And then once I get to right where my cursor is, the flow is high enough that my minor losses are going to get too large. And so I need to pop up to the next size tubing, which in this case would have been 3/32 of an inch. And that works for a while. And then that tubing starts to have minor losses that are too high. And so I pop up to the next size tubing and keep on going. Questions about that? About all the information that's packed on this one graph, showing the constraints and showing what real designs you could actually use? And for the first time, giving you a sense of how small these tubes need to be. They're order 1/8 of an inch in diameter in order to get this both laminar flow and also keeping the minor losses low. Any questions on that? The next graph just shows a crazy response that you might not have anticipated. And this is, what about the length of the tube that's required to get you the flow through that tube? So we need a tube that gives us 20 centimeters of head loss. So that 20 centimeters is somewhat arbitrary, although it's a nice number. It's nice in the sense that it's the same number that we're using for the linear flow orifice meter. So it's nice to have those two work together. And both of those could be larger, could be smaller. And you should always be wondering, well, what then selected, why was 20 centimeters chosen as the perfect design for arbor-clada plants? If we go to more head loss through our linear flow orifice meter and through our dosing system, that ends up meaning that the head loss through the entire plant increases because all the water goes through the linear flow orifice meter. So if we increase the height of that, that's more head loss through the plant, a bigger elevation change across the plant. And that essentially means that the building that the plant is in needs to be taller, because all of the difference in elevation and water in the plant has to be accommodated inside the building. And so if you increase the difference in water between the low end of the plant and the high end of the plant, the building needs to get taller to accommodate that extra height. So it actually costs you money every time you add more head loss to the plant. So that's one reason not to make the head loss really large in the linear flow orifice meter. So then what's as small as it can be and still have it work nicely? I feel like this is kind of a human scale question. Like, it should be nice for an operator to read a number off the side of the entrance tank and know what the flow rate is. It has to be small compared with surface tension effects. There's going to be a surface tension effect on the dosing side where the chemical exits from the dosing tube and drips down and does a free fall. There's a surface tension effect there. So it needs to be something that the height that we have for the head loss has to be much larger than the surface tension effect. So all of that says that 10 centimeters for an LFOM is actually tight. Like, you can make that work for small flow plants, but it's tight. 20 centimeters is nice. If you wanted to have a system with even higher accuracy, you could go to higher head loss. You do get more accuracy as you increase that head loss. Okay, so now we've set 20 centimeters as our head loss. We have a tube that we want to have carrying on the flow that's required for our chemical feed system. And now we need to figure out how long that tube needs to be to get us that target flow rate. And the equation is there in green. And what happens is if your flow is lower, the tube has to get a whole lot longer to create enough head loss. And so that's why these green lines have this crazy, very sharp curve. You would end up having to have a really, really long 1/16 inch diameter tube if you wanted a really, really low flow rate through that tube. So this is going to be, it's going to want to encourage us to try to create designs where we're actually having flow rates that are close to the maximum that a tube can carry, so that the tube can be short. But you understand that if I want to make a dosing tube and I want to put less flow through it than what its maximum is that it can handle, I'm going to have to make it a whole lot longer so that it can still create the required head loss. I would love to have like thumbs up, thumbs down, thumbs crosswise for that question. Does the fact that the tubes have to get long when we have lower flow rates, does that make sense to you? Okay, so there's still some question on that. So let me think about, does anybody who understands it want to pitch in and give like another take on why does the tube have to get long if it has a lower flow rate? Okay, how about we just change the question? If I have variable flow that I can adjust the flow through a tube, and I'm measuring the pressure drop across that tube. If I increase the flow and the pressure drop across that tube then increases, I could reduce the head loss in that tube again by cutting it shorter. Right? If I increase the flow, but I want to get back to the same head loss, I could just make the tube shorter. Do you buy it in that direction? Okay, and this, I was just saying it in the other direction. In order to get the head loss, I have to make it longer if I have a low flow. Ponder that one. You can always ask me the question again in your email that you're going to send me at the end of class. So here's how we design. We take the set of tubes, different sizes of tubes that we want to evaluate for their feasibility. And we calculate the maximum flow rate that each of those tubes can handle, given a target of having less than 10% error due to minor losses. So there's the equation for the maximum flow that you can have through a tube. It's a function of the tube diameter and a function of the minor loss coefficients that you're going to have for your dosing tubes, which might be on the order of 2, an entrance loss and an exit loss. You need to know for your system, what's the chemical flow rate that you actually need? So given a plant flow rate, a coagulant dose, a chlorine dose, the stock concentration that you're going to be using for both of those chemicals, how much chlorine and how much coagulant do you actually need to provide? And then you have the maximum flow. So now you take that maximum flow. This is the maximum flow that you need, and you divide it by the flow that each tube can handle. And you would end up getting the number of dosing tubes. And you could do that for all the different sizes of tubes that you have available. And so you get the number of dosing tubes that you would need for all the different sizes. You calculate the length of the dosing tubes using that long equation. And you could do that for each different size of tubing. And then you could say, okay, let's let some reality check in here, and you would select the longest dosing tube that is shorter than the maximum tube length that you can fit into your plant. And you'd select the tubing diameter that comes from that size, and then you'd know what your flow rate is through that selected tube length. And you would also know from one of the previous steps how many of those dosing tubes you're going to need. So the idea here is that you're going to end up in many, many cases requiring more than one dosing tube working in parallel to get you the required flow of chemicals. A few reflections on accuracy. There are many places where a little bit of error shows up in this system. One of them, float valves don't actually provide a constant level. They provide a close to constant level. They greatly attenuate the change in level that's happening in the stock tank and get it down to a tiny little fluctuation inside the constant level tank. And that change is probably on the order of a few millimeters, which is why having a total head loss on the order of 20 centimeters is good, because it means that the 20 centimeters is large compared with the few millimeters of change in the constant head tank, constant level tank. There are surface tension effects where the chemical exits from the dosing tube system and goes into that drop tube, the Niagara Falls situation where there's supercritical flow. Right where that exits, there's a potential for surface tension to be kind of grabbing a hold of those droplets and providing variable pressure back on the dosing tube system. That could cause errors of a few millimeters at most. So it's another reason to have head loss that's order 10 or 20 centimeters. And then this last one is, I don't know, I think it's fun to think about the physics of this. The weight of the tubing that's hanging on the slider that's supported by the lever, and the weight of the slider itself will apply different amounts of torque to the lever arm depending on the dose that's chosen. So you get this lever arm and there's this slider that's hanging off of it. And as I move that slider back and forth on the lever arm, the amount of torque that it's providing is different. As clearly as if I'm close to the pivot point, I'm not providing any torque. If I'm far from the pivot point at a high dose, I'm providing a lot of torque. And that means that it's going to move that lever arm a little bit. And what's resisting that motion at the other end of the lever, there's a float, and that float is hanging out in the water. And when you move that float up and down in the water, you get a force that's related to the change in depth times the surface area of the float and times the density of water and times gravity would get me a weight. So I'm curious, what do you think? If I want to have a system that is as accurate as possible, do you think it would be good to have a big float sitting in the entrance tank or a little float sitting in the entrance tank? So the little float is, or this float is what's moving the lever system up and down. Do you think it should be a big float or a little float? I'll give you like 15 seconds and then we'll just do a show of hands for both of those. Okay, let's vote. So who would like to vote for a bigger float would improve the accuracy of this dosing system? Who votes for using a bigger float? Hands up. I see 1, 2, 3, 4, 5. Okay, and who would like to vote for a smaller float would improve the accuracy? So I have 1, 2, 3, 4, 5. I feel like we're at almost exactly the same, although there are a number of people who have abstained. So I want to say that you are in really good company. We have had very bright Cornell engineers in the field being completely confused by how this works. So now, what was one of Monroe's tricks for when you're asked a question like this? What's a trick for figuring out what the answer is? Anybody remember?
Use extremes.
Use extremes, okay? So what happens if you use extremes?
Would we use like a really big float and then like a really, really small one?
Yes. And what happens Well, what happens when you use a really, really big one? Do you think the doser would still work? I mean, it does have to fit in the entrance tank, and that actually is a constraint. What happens if you make a really, really tiny one that goes down to non-existent?
I think if the float was too small, it would be too affected by the weight of the slider and the tube. And then if it was large enough, it would be it would only rely on the level of the tank to move the level of the water.
That's exactly right. So if the float was close to non-existent, you would move the slider, and the slider would, if supposing you had this working and you had the slider set at 0 dose, and then you move the slider down the lever arm towards the end, that provides more moment. It's pulling harder because your float is so tiny, it's just going to pop it right out of the water, and it's no longer going to track the water surface. Do you all buy that? So bigger float is better. And the only thing that prevents us from going really large is actually economics. A bigger float is better. Yay. So now if you go to the field and have to work with one of these, you will not trim the float to try to make it work better, because that never helps. Making the float smaller never makes it work any better. It only makes it worse. Okay. So how much can you get out of one tube? If we only were to use one tube, and we used a 5mm diameter dosing tube, which would end up requiring a pretty long tube, but could work. That ends up being about 8.7 milliliters per second of flow. This is basically keeping the minor losses small. And then, oh, this is the QC equation. So this is the equation that a water treatment plant operator has to learn in order to effectively understand what's going on in a water treatment plant. So it's only fair that if you're going to design a water treatment plant, you should also know the QC equation. The QC equation is really mass is conserved, okay? You could think about m dot. The mass rate is equal to the mass rate. That's all this is saying. Q is the flow rate. C is some concentration. And it's got to be the same whether you're measuring the chemical feed system or what's happening in the plant. So there's a little tube that's coming from the stock tank and is going down and then is dosing chemical into your plant where it's blending with the whole flow. So that little tube that's carrying the chemical, if you take its flow rate and its concentration, multiply those two together, that's the same as you get if you take the plant flow and its concentration. Okay, so QC equals QC. So I can take that and I can solve for the flow of the plant given the inputs that I gave, where there's a polyaluminum chloride, the coagulant concentration in the stock, and the dose. Notice that there's a big difference. One is 160 grams per liter and the other is 30 milligrams per liter, which is, you want that because you would like it if your stock tank would last for days and not have to be huge. So you want the chemical stock to be very, very high concentration compared to what you're actually using in the plant. So all this analysis suggests that by the time you get to about 50 liters per second, you're going to need more than one dosing tube. So that's the solution, more than one dosing tube. And actually it happens even before 46 liters per second, because even using a 5mm diameter tube ends up being larger than what's really convenient because it ends up being so long. So there's things that can be improved with this system. So designing it so that it is easier to clean, perhaps making it possible to clean it in place is one of the things that I want to be thinking about. Like if we could design a system that they could easily empty out the chemical feed that's in a set of tubes, and they could dump some vinegar in there and let it sit there for a few minutes and then drain it out and then flush it out with water and then replace with the chemicals they're normally using. If they could do that without taking anything apart, that would be a very nice improvement to the design. And another thing that I learned about a year ago that they don't like is they don't like having 6 dosing tubes, each with their own valve, and each need to be taken off and cleaned independently. And so we've had this idea of a bundle of tubes that are inside a pipe. So that's just a sketch of the idea, obviously not drawn as long as it would be. This might be 1.5 meters or 2 meters long, but would have a bunch of small tubes shoved inside of this larger pipe. And the idea is that you're creating all these small flow passages so that you can get laminar flow inside this larger pipe. And that way, when you need to clean it, you would take that whole bundle of tubes offline and you would soak the whole unit at once as one unit in vinegar. You could imagine a system where you have a pipe that's 2 inches in diameter with a cap on the end that's full of vinegar, and you just drop this tube down in that bath of vinegar and clean it that way. That's a design that's waiting to happen. One of the big constraints is that whatever you use, it has to be chlorine resistant, at least on the chlorine side. The coagulant is actually not nearly as difficult. It's just slightly acidic, but it's not corrosive in the same way that the chlorine is. It would be awesome if there were a way to fill up a pipe with a honeycomb structure, right? A hexagonal structure. That would be really, really sweet, but I don't know how to do it. And there's limited materials that actually work with chlorine. PVC is like the best material for working with chlorine. And there's like Tygon tubing is also PVC tubing that's just flexible. So both flexible PVC and hard PVC both work well. If you switch to any other plastics, you're gonna have more trouble. And the only other plastics that are viable are things like Kynar or Teflon-based products, and those are far more expensive. So figuring out how to fabricate this tube in a pipe or whole bundle of tubes in a pipe is a thing that is still waiting for some innovation. Which means that there's more for you guys to help figure out. So my summary of all this related to dosing. We need these 2 systems, laminar tube flow and for our dosing tubes, and we need a linear flow orifice meter. There are opportunities for improvements on both of those. We need a new LFOM design for flow rates above about 100 liters per second. So once you get up to higher flow rates, you end up with like 18-inch diameter or 2-foot diameter PVC pipes, which are very awkward to work with. And if you think about the idea of the LFOM was that it was just shoved into a coupling that was buried in the concrete in your entrance tank, like the one that you designed. And the idea was that you could actually take that LFOM out of the tank if you wanted to. Once you go to a larger plant, that's not going to be possible because a human cannot lift a 2-foot diameter PVC pipe out of a coupling. It's going to be in there too tightly, and you just can't do it. And the 2-foot diameter, 24-inch, 60-centimeter diameter pipe is also quite expensive. So it begins to make more sense to think of another way of fabricating the LFOM rather than using a pipe. And it would argue for doing something in concrete, making a channel with a weir where you have this, or maybe it's a PVC plate that's an insert into a concrete wall, and you do all the hole drilling in that PVC plate, but it's just like one long flat plate. There's a need for some innovation there. And like I was talking there's a need for a better dosing tube design for high flows as well. But what's good about it? These devices are robust. There's hardly any moving parts. They need to be designed so that there are no small parts to lose. I'll give another example of things that we learned. Early on, we were experimenting with what connection system do we use to connect between the small tubes and other plumbing pieces. And we got some quick connect plumbing, and those quick connect fixtures have little parts that can come apart. And we just very quickly realized that's a disaster, because eventually they do come apart, and then you have little parts rolling around in this big, like, industrial kind of complex, and they get broken or lost very, very quickly. And so small parts that are easily lost are just not a good idea. It has to be compatible with chlorine, and you got to watch out for every place where there's O-rings. We'd like to use locally sourced materials when possible. So if the Tygon tubing that's available in country is PVC and it's relatively resistant to chlorine, that's a great option. The fittings are actually the real challenging part, like getting the barbed fitting that will connect between the dosing tube and some other part of the plumbing. That's where we're still running into difficulties, and where we think that we end up having to source those here because they're often not available in country. I didn't show you, but we have the equations for the viscosity of both the coagulant. The coagulant viscosity changes quite dramatically as the concentration of the stock increases. I don't actually have any good data on chlorine solution viscosity, but my first order guess is that it's very close to water, because the chlorine stock concentrations are quite dilute and they don't have this polymer effect that the coagulants have. And just drilling this home, minor losses have to be minor in this system, because minor losses go with the square of the velocity, and we want the linear system. And chlorine is going to deposit calcium carbonate, so that has to be easy to clean. I did learn recently that there are other chlorine compounds that are based on sodium that are also sold as solids that would be a possible replacement for calcium hypochlorite, but they're not commonly available. They're made in the US, and I haven't seen them in other parts of the world. The other option would be to use bleach. Like, bleach is sodium hypochlorite. You can buy bleach at the grocery store as a liquid. That is actually a really nice chemical to use as a source of chlorine. Many of our local water treatment plants use that instead of using chlorine gas, because people don't like to die from chlorine gas, and so they don't like to use it. But bleach, it's much harder to die from it, so much less hazardous. So bleach is great, and bleach doesn't deposit any calcium carbonate because it doesn't have any calcium, it has sodium. So that would be a great chemical to use. And now you're wondering, well, then why don't we just use bleach instead of calcium hypochlorite? And the reason is because you can buy solid granular calcium hypochlorite, and the amount of chlorine per mass of calcium hypochlorite is much, much, much higher than the amount of chlorine per mass of bleach. And so if you're thinking about transport, then the cost of transport of getting this chemical to your site, to your water treatment plant, the costs are lower if you can use calcium hypochlorite. So that's the reason why we're using calcium hypochlorite in Honduras, well, in Central America, and indeed in India as well. And that is the end of that. And I'm happy to take any questions. And otherwise, I'm feeling really, really happy. And we're going to actually start just a little bit early on the notes related to flocculation. But I'm happy to take any questions that people have about that dose controller system. By the way, is the background noise bothering you? Okay, good. There's two of us teaching in this house at the same time, so it's all friendly, but. Okay, so if there are no questions, I'm moving to flocculation introduction. And I get so excited because flocculation is like my favorite topic. Actually, it's hard for me to tell which actually is my favorite topic. I love multiple of these treatment processes because they work so nicely together. So here comes flocculation, and I will need to get my screen arranged and share it. Here we go. So what I want to do, and Patrick, you can make sure that you remind me at 3:30 to stop talking, okay? So flocculation. So we're going to talk about how do we separate contaminants from water, because there's some things in the water that we don't like. Yeah, we figured out how to measure the flow. We know how much is coming into our plant, but there's some things in that water that we'd like to get out, and that's the whole point of this course. And we'll discover that sedimentation is a really awesome separation technique, but it's too slow for a lot of the things that we want to remove. And so we're going to figure out how to gang up on gravity using flocculation. And we're going to talk about sticky nanoparticles. So these are, if you're going to separate two things, there has to be something different between those two things so that you can separate them. And the differences might be, the color or the density or electrical charge or something. So here are options for differences that you could potentially exploit. And you'll see that even though there are many different things that we could potentially measure, and I guess I should have added something like there could have been smell, right? There could have been some other interesting characteristics that we could have used to separate things. The ones that we end up using in our water treatment plants are really size and density for the processes that we're covering in this class. There would be a whole other class of things that we could talk about related to using things like activated carbon or ion exchange resonance. But even if we went down the path of thinking about membrane filtration, or if we thought about reverse osmosis, we'd effectively be talking about size. We're using the fact that the water molecules are tiny compared with some of the other molecules that we're trying to remove in those cases. But we're talking at an even bigger scale, still small scale, but even bigger scale. We're going to use size and density to remove things. And let's go to the problem. We'd like to use sedimentation to separate out the particles that we don't want. We'd like them to drop to the bottom or float to the top, I suppose. And so there's our little particle, and we're going to look at the forces that are acting on it. And we know that the sum of the forces equals mass times acceleration, but this guy is not accelerating. So I suppose we're going to say that there's a couple different forces acting on it. There's its weight that's pulling it down. It's gravity acting on it. There's a buoyant force that's tending to pull it up. And there's a drag force that's tending to pull it up, assuming that this thing is moving down. And so those three forces have to sum to zero because it's not accelerating, okay? And the weight of this object is just equal to its volume times rho and g. So the density, and here I said I'm talking about a flock. So the density of the flock and times the acceleration due to gravity. The buoyant force is just the volume of the flock times the density of water times gravity. You probably remember buoyant force from fluid mechanics. So that's the net force acting up, or the force acting in the upward direction. And then there's this drag force, and this drag force equation comes from fluid mechanics. It's dimensionally correct, makes sense. It's some coefficient of drag times the projected area of the flock, and times, and it's interesting, this drag force the density that's in that drag force equation is the density of the fluid, because the drag is caused by the fluid. So it's not about the density of the flock. Is that clear? If you're thinking about the drag force on your car when you're driving down the road, the density of your car has nothing to do with it. It's only the density of the air that matters. So in the same case here for our flock, the density that matters is the density of the fluid. And then of course, times its terminal velocity, it's velocity squared over 2. So we can set all those, you can use FD plus FB minus W, the force of drag plus the force of buoyancy minus weight is equal to 0. We've got equations for those 3 forces, and we can solve for the terminal velocity. Okay, so I just tuck those 3 equations together, solve for the terminal velocity, and I have this beautiful general equation for how fast will a thing that can be characterized by a diameter fall. And so if you could characterize a human as spherical, this would work for humans falling in air, as well as for a cryptosporidium that's settling in water. It all works. And then here's the next part, and that is this drag coefficient is like the big unknown, and that's what's needed to solve this equation. The drag coefficient, unfortunately, is not a constant. It's a function of the Reynolds number, and it's a complete mess. And I would love it if you would see that this graph is so similar to one other big graph that I showed you in this course. Anybody remember which one? This graph is a lot like, who wants to be brave? There was another graph where there was a linear region where it was laminar, and then there was this crazy, yeah, somebody's talking now.
Is it the Moody diagram?
It is the Moody diagram. So yes, it's describing exactly the same thing as flow through a pipe. It's just that this time it's flow around the sphere. So the geometry is a little bit different, but in both cases it's flow, and the fluid, the laminar and turbulent makes a big difference. And in both cases, it acts completely different in laminar than it does in turbulent. And in both cases, it flattens out at high Reynolds number, with the added complication that there's a little bump in this curve out around like 100,000, it's high, and then it drops down by the time it gets to about 300,000. And that little bump is when the boundary layer around the sphere gets turbulent. And just because I like fluids, I'll have to bring in this a little aside. This is why, if you play golf, the golf balls are dimpled, because the dimples on the golf ball help the boundary layer transition to being turbulent a little bit earlier than it normally would be. And it makes the golf ball have a turbulent boundary layer. Turbulent boundary layer means the boundary layer gets a little bit smaller, and that makes the wake behind the ball a little bit smaller, and so it has lower drag. So this is an odd effect where turbulence in the boundary layer actually makes lower drag on an object. And so now, because all of you are extremely interested in saving the planet, right? Like you're trying to reduce how many fossil fuels you use, and you're trying to, I don't know, reduce, or you're trying to improve the efficiency of your car. And so now you're thinking that you're going to go out to your parents' car with a ball peen hammer, and you're going to put little dimples throughout the car so that it gets better fuel mileage, right? Now I realize I'm going to be in really big trouble, because some of you are going to do this later today, and then there's going to be all these unintended consequences. Okay, so anybody know why that's not going to help? I'll give you a hint. Your car is bigger than a golf ball. Do you know what that means? The car is bigger than a golf ball and they actually travel at similar speeds. So what does that mean?
Mass plays a role.
No. Where's the car on this curve? Because it's bigger and still traveling fast. This bottom Reynolds number is V times D over nu. So V is how fast the car is traveling. D is, okay, some width of the car or height of the car. And you're comparing that with a golf ball. So the Reynolds number for a car is higher, given if it's traveling at a similar speed. So the car already has a turbulent boundary layer. And so putting lots of dents in your car won't actually help, and it might cause some people to be angry with you. Okay? Now you know why you won't take the ball peen hammer to your car. Okay. Happily, like this equation, this is a mess. This is just like on the pipe side, using the Moody diagram was a complete mess. And I told you, please don't use the Moody diagram, use equations that capture that instead. We'd like to do a similar thing here. And what's going to save us here is that most of our world with removing particles in water treatment processes is small enough and slow enough that it's all in the laminar range. And so we can use that laminar range where it's just a straight line on a log-log plot. And we can use Stokes' law. And just like on pipes where there was 64 over the Reynolds number showed up as this nice relationship for F, for laminar, here coefficient of drag is 24 divided by the Reynolds number. So another beautiful, simple relationship. And that means that we have two different equations that we can use. For turbulent, we just take, hang on. For turbulent, we just take this equation that was at the bottom of the previous slide. Okay, that is the general equation. It's always true. It's like Darcy-Weisbach. It's got an F in it and it's always true. This one has a coefficient of drag in it and it's always true. For the specific case where we have laminar flow, we can replace the coefficient of drag with 24 over the Reynolds number, and we can replace the Reynolds number with the velocity times the diameter divided by the kinematic viscosity. And when you do that, you get velocity shows up on both sides of the equation, but happily, you can easily factor it out again. And so you can solve for velocity and you get the new equation that I've shown now at the upper left of the slide. And so that is a beautiful, simple equation that only works in laminar flow. It's like the Hagen-Poiseuille equation in pipes. And it's going to be very, very useful for us. We're going to be using that equation plenty of times. And here's the question. Given that that's the equation, will a bacteria cell settle fast enough that we can just use sedimentation to get it out of the water? And so this is just taking that equation and plugging in like order of magnitude estimates for the various things. So a bacteria cell is 10 to the minus 6 meters, right? It's a micrometer in diameter. So when you square that, you get 10 to the minus 12. G is about 10. The density of a bacteria cell is it's close to 1,001 kilograms per meter cubed. And the density of water is 1,000 kilograms per meter cubed. And so you end up with that whole term, rho bacteria minus rho water over rho water ends up being 10 to the minus 3. Because that small difference between water and bacteria. Viscosity is about 10 to the minus 6. and you crank all that through, and you get a terminal velocity that's it's on the order of 10 to the minus 9 meters per second, which is a nanometer per second. And I don't know when the last time was that you watched, a race that was happening at a nanometer per second, but it's kind of boring. And we basically can't afford to wait. And there's another problem, and that is when you are settling this slowly, there are other things that are happening that are moving you around randomly that are going to end up mixing you back up. And that is something that we have no experience with as humans at our scale. But at the scale of a bacteria cell, you notice it when you get hit by a water molecule. And you actually move a little bit every time you get hit by another water molecule. So diffusion, molecular diffusion, the fact that water molecules are bouncing around because they've got thermal energy, that's moving the bacteria around as well. And that means that, and that rate is actually faster than this terminal velocity. And that means that diffusion is going to help keep that bacteria cell in suspension, and it's never going to settle out. So that was grim, and it would suggest that if we're trying to remove pathogens from water, sedimentation is not a good option. But we're going to apply a trick. How could we somehow mess with this equation so that we could improve our ability to remove things? So our problem was that the terminal velocity was much too small. So how could we increase the rate, the sedimentation rate for small particles? How could we get small particles to settle faster? And what you can do here is you can use this equation as a guide, because every single term in this equation provides an opportunity to do something. Every term except the 18. You can't mess with the 18, right? 18 is 18, but everything else you can mess with. So what might you do? Give me an example. What might you do to increase the sedimentation rate of small particles? I'm going to call on Stephanie, because I haven't heard from Stephanie for a while. Do you have one that you could think of?
I'm sorry, could you repeat the question?
The question is, how could you increase the sedimentation rate of small particles?
I guess this is, well, by adding coagulant.
We're going to apply that trick, but what's that doing? How is that changing something in this equation?
You're increasing the diameter.
Excellent. Okay, so that's one trick. Thank you, Stephanie. We could change D, and I don't remember which order I actually did. Yeah, so that's one. What else could you do? Maybe do you guys all have this presentation open on your computer so you know all the answers already? No, I mean, and that's completely legit. I put them online. What else could you do? So Stephanie took care of, she played with that first term. I'd love to give Preston an opportunity. Which one would you change?
The term in the denominator that's attached to, I don't know.
The one next to the 18, is that what you mean?
Yes. Yeah.
Okay, so that's new. the Greek letter nu, and it's the viscosity of the water. So how would you change the viscosity of the water?
You'd have to add something to the water. I don't like it. You'd have to change the chemical, like, you know,
Okay, so maybe you could add something to the water. It's relatively easy to add something to the water that would increase its viscosity, but it's hard to add something to the water that's going to decrease its viscosity. And I'll open it up for anyone. What could you do to decrease the viscosity of the water? Because, right, you want to increase the terminal velocity, so you've got to decrease the things that are on the bottom of this equation. What could you do to decrease viscosity of water?
Could you increase the temperature?
You could increase the temperature. So we're going for everything that's possible from a physics standpoint. You could absolutely do this if you heat water up, viscosity drops, and then things would settle faster. That's physically true, but it's not practical because the amount of energy required to heat up water is actually really, really high. And so you are not going to be heating up all the water going through a water treatment plant. It's not viable. That was good. Who wants to pick the next one? Let's see, it's time for Isaac.
Similar to a bigger D value, could you make a bigger G value?
How would you do it?
That's a great question.
I have a big D value.
I mean, just think outside the box. Think of ways you could do it.
Could you change this, like where you're, like the area that you're in?
Yeah, and if you really wanted to, like, you have to like really think outside the box. How would you go somewhere where there's a higher G?
Either go higher or lower, change like the elevation maybe.
Okay, there is a tiny effect as you change an elevation, but think outside the box. Like really, what would you need to do? Where could you find a much, much higher G?
on Jupiter.
Yeah, let's go to Jupiter. If you put the water treatment plant on Jupiter, then particles would settle a whole lot faster. So far, there's a limited market for this, but that's the answer. Now, if we come back to home and we say you're limited to doing it on Earth, what else could you do that's kind of cheating, but it also is basically increasing an acceleration?
Could you spin the particles really fast?
Yeah, you could make a higher effective G by sticking it in a centrifuge. And that's also, that one is more viable than going to Jupiter. And indeed, running suspensions through centrifuges is a separation process that's used. Not, as far as I know, it's never been used on, I shouldn't say never. I just say it's not a standard practice for drinking water treatment, but it's a possibility. Okay, and I got one more minute. Who wants to jump in with one more thing that you could do? Katie, do you have one?
You could change the density of water by like changing the temperature again.
Ah, that's right. You know that there's a relationship between density and temperature. And so you could, let's see, you might want to decrease. No, you would like to increase the density of the water. No, you'd like to decrease the density of the water. Thank you, Ravi, for that good feedback. You would like to decrease the density of the water so that the particle would settle faster. Okay, well, look, that was great. So now, thank you. And thank you for being game, for having me actually call on you. It was nice from my side because that way I got to hear from more of you. I would now like to give you this kind of open-ended task of sending Monroe a little email. And in order to do that, you need my email address. Do you guys know my email address? I mean, I know you don't have it memorized, but I will pop it into the chat. And the question that you're going to answer is, what would you characterize as something that is going well for you in this course? And what is something that you think could be improved? Is that good? Just two things? I want it to be completely open-ended. You could do whatever you want, but those are like two starter questions. What is for you going well in this class? What could be improved? And as a third thing, a question that you have that you haven't yet asked that you would like to ask. Got it? What's going well? What could be improved? A question you have. Send me an
Monroe, can I
email.
jump in?
Yes, please.
I want to make a slight suggestion.
Yes.
Unless you would love to have them all email, could we
It's
do
fine.
this via Google form? That way we can have it in all one place moving forward. And then next autumn, when we're thinking about how can we make the class better, it's right there.
Sure. Are you game to make a? Are you game to
Yeah,
make one
I
real
have-
quick?
I have one that is those questions I used for the other class, so it is already in the chat.